Welcome to Science, Technology in the Future, and happy Future Day being March 1st. The sad news is that theoretical physicist and mathematician Freeman Dyson has recently passed away. So, in celebration of Freeman Dyson's life and his achievements, the good news is we have the privilege of tapping Anders Sandberg's brilliance he's from the Future of Humanity Institute in Oxford. He is a seminal transhumanist thinker from way back who's contributed a vast amount of mind-blowing material to futurology and philosophy in general. This discussion is a fast-paced deep dive. It gives a background into Freeman Dyson's life, his influence on how Anders thinks and how others think about the future, which influences how we think about how civilizations may develop. We discuss strategies for harvesting energy, star engulfing Dyson spheres or swarms, black hole swallowing tungsten Dyson megaswarms, as well as other galactic megastructures. We also discuss Kardashev scale civilizations. Now, Kardashev was another great mind who we lost recently, unfortunately. We discuss birthing ideal universes to live in, Meinong's jungle, eschatological engineering, the aestivation hypothesis, and how all this may inform strategies for thinking about the Fermi Paradox and what this might suggest about the likelihood of our civilization avoiding oblivion. Though Anders is more optimistic than some about our chances of survival. So if you enjoy this, please press like and subscribe. Welcome everybody. I've got Anders Sandberg here, who's polymath extraordinaire at Future of Humanity Institute. Many of you may have heard of him, and we've done interviews in the past. Actually, we did some in Oxford itself a while ago. And Anders, you've got a grand futures book in the pipeline at the moment.
Yeah, thank you for having me here. So the biggest problem with this book is, of course, it's so enormous because I'm trying to write about what are the limits of what intelligent life could do in the universe. And unfortunately, those limits are rather wide, which means that right now my book manuscript is expanding at a rate slightly slower than the expansion of the universe, but not by much.
Nice. Well, yes, we unfortunately recently on the news we've heard that Freeman Dyson has died. And Freeman Dyson is, of course, a theoretical physicist and mathematician who is well known amongst futurist circles to have come up with the idea of a Dyson Sphere, which is catalyst for this interview. Have you got any thoughts about this Freeman Dyson's life and how he's influenced your thinking, Andrew?
So Freeman Dyson has had a huge influence on me in many ways. I was lucky enough to actually meet him in person in Princeton a few years ago. And there was that general problem of, oh no, I'm meeting one of my idols, I'm not worthy. But he was a very kind host, and over some apple pie I was describing what I was doing with my book, and he was nodding politely and then pointing out that I should probably add some stuff about evolution too. So he was certainly not helping me shorten the book. And I'm referring to him in many of his capacities. So as you mentioned, the Dyson Spheres might be the most famous construct among futurists. The idea that one could englobe a star with solar collectors and get a hold of the energy. But many of his other ideas also show up. In the late 1960s, he managed to prove the stability of matter, which really shows his genius, because most people would say it's obvious that matter is stable. We're around, right? But it turns out that when you actually try to think about it carefully using quantum mechanics, it's not at all obvious that it can hold together. Maybe it should just implode very quickly to low energy states. But it doesn't. And the reason why tells us complicated and profound things about the kind of physics we have. But he also shows up in game theory, what forms of cooperation might be possible. He shows up in physical eschatology. So this term was invented by Martin Rees, the astronomer royal, also in the late 60s. Eschatology is the part of theology that looks at the end of the world and the meaning of life, the ultimate things. And Rees had written a paper about the collapse of the collapsing universes, and he pointed out that we could maybe call this field physical eschatology. So that was the coining of the name. And astronomers in the 60s and 70s started realizing that you can say a few things about the far future of the universe. And then in 1979, Freeman Dyson wrote the seminal paper about life and structure in an open universe. This was a mind-blowingly powerful paper where he demonstrated that using known physics, we can actually make conjectures and even some predictions about the far future. But we can also start talking about the role of life and intelligence in shaping the universe.
Mm-hmm.
So that was a seminal paper which strongly influenced another book which made me the futurist I am, The Anthropic Cosmological Principle by Barrow and Tipler, which again is borrowing very heavily from Dyson's paper. But even today, when I go back and reread some part of the paper, I'm discovering new things. A throwaway remark, and that's enough to send me off in another theoretical rabbit hole. It's so dense with insights.
Indeed, wow! There's a lot of papers out there that I didn't know. That's incredible, and of course,
So Freeman Dyson, of course, was amazingly productive. So if you go to almost any area of science, you will find that he's been around there. So of course, quantum mechanics and quantum field theory and scattering theory, they are all familiar with Dyson series and that stuff. But then you have discussions in the search for extraterrestrial intelligence where people even speak about the Dysonian school of SETI. So the traditional idea of SETI was, let's build a radio telescope and listen for messages from aliens that might be sending something to us. And this is based on an assumption that maybe the aliens are like us, that is, radio astronomers trying to look for alien intelligence. Which maybe makes sense, but critics pointed out that besides that maybe the universe is bigger and emptier than they thought, we can't be certain about the motivations. Another school emerged, and this is what is called the Dysonian SETI, saying maybe we should just look at kind of their industrial waste product or their industrial activities. So in his Dyson Sphere paper, and of course, Freeman was always adamant in pointing out that it was not his idea. He had totally borrowed it from Olaf Stapledon's novel Star Maker.
Yes, yeah.
So he preferred to call them Stapledon spheres or Stapledon habitats. But there he pointed out that if we extrapolate current energy uses for humanity, within a few centuries, we are going to be requiring as much energy as the sun produces. And maybe that's a logical endpoint, that civilizations absorb all the energy of the star. Now, if you put solar panels into orbit, you can actually get that. In a sense, we have already started on our own Dyson Sphere with the various observatories and satellites in heliocentric orbit. It's a very tiny and puny Dyson Sphere, but the current acreage is probably about the size of a football field or even smaller. But still, it's there. And Freeman's point was we could observe these installations because they would be emitting infrared radiation rather than the visible light. So they would look somewhat strange, like big, cool objects that still emit a fair bit of energy. So he suggested that maybe we should look for these kind of things instead of the radio signals. Because if you want, as an alien, to figure out whether intelligent life on Earth, there are very few messages we're deliberately sending, but our street lights are certainly sending a signal, even though they're mostly intended to keep us on the roads during night. So similarly, the Dysonian approach to SETI is based on, let's look at the side effects of the vast activities advanced civilizations might be doing.
Indeed. And is it still thought that it would be infrared radiation that we should be looking for, or is it something else today?
So today, in the search for extraterrestrial intelligence, there are several branches.
Yes,
because we can now observe in many more wavelengths. Yeah. So the thing is, detecting these kind of megastructures would require, of course, a good infrared telescope. And by now we actually have had a few launched into orbit, and sadly we have not been able to detect anything like that. It also inspired something called the J-HAT survey that looked at about 500,000 galaxies and their light curves to try to see, is an appreciable fraction of the starlight in this galaxy absorbed by something and re-irradiated at cooler temperatures. It doesn't seem to be true for any of the galaxies surveyed, so it doesn't look that there are any kind of galactic level super civilizations around at least our neighborhood of the universe. But the interesting thing is you can expand that to other forms of megastructure. So we have recently become very good at looking for exoplanets, which of course led to the discovery that some stars have very weird light curves. There is one that is quite often nicknamed the Tabby star in
Yes.
media.
That's
That has
good.
this very weird light curve, and people have been debating maybe that's a weird alien megastructure, maybe that's a Dyson Swarm under construction, or maybe it's decaying. I find it very unlikely because the time it takes to build a Dyson Swarm or for it to decay if nobody maintains it into the disk of dust and planets is so short compared to a stellar lifetime that we're unlikely to see it happening if we just look at a random point. But it shows that people are taking it rather seriously, and we're certainly learning interesting things by examining these exotic objects. Because thanks to a better telescope, we're finding that the universe is much more fantastic than we ever imagined, which of course made Freeman very, very happy because he pointed out in one of his writings that maybe the universe is maximally interesting. So far,
Interesting.
that seems to be borne out rather well.
Yeah. So, I mean, so what other galactic megastructures can you imagine a civilization might want to build other than Dyson spheres, like or Dyson swarms, or Dyson bubbles?
It's worth kind of untangling that terminology a bit.
Yes.
So normally when we talk about a Dyson sphere, it's collectors that collect all the energy from a star. And it doesn't say exactly how they're arranged. So one naive idea might be, let's just make a spherical shell totally solid around the star. And this feels rather natural, except that it doesn't work at all. And it's actually quite a fun physics challenge to see why it doesn't work. Basically, the total force of a star on the shell is kind of balanced. So if you push the shell to the side, some parts get further away from the star and other parts get closer. So the net force is zero. So the shell doesn't stay centered around the star. Even worse, the stresses inside the shell because of the gravity nevertheless are enormous. So it turns out that you can probably not build this out of normal matter. It would probably tend to buckle rather badly. What you instead can do is make a Dyson Swarm. You have freely orbiting solar collectors, and they might, of course, be pretty big things. They might be continent-sized or planet-sized for all we know. But you put a ring of them around the equator, and then you put another ring tilted a little bit, and another ring tilted, all with slightly larger radiuses. And that way you can capture most of the energy from the star. But you might even want to go lightweight. So you could imagine to use a very thin aluminium foil, so thin that the light pressure pushes it away from the star as strongly as gravity drags it towards the star. That's called a statite. And on its own, it's kind of pointless because it just hangs there. But you can make it slightly bent. So now it acts as a parabolic reflector and focuses the starlight onto some collector. And then that collector needs to be connected through some strand to an outside thing that radiates away waste heat. When you do the calculations, you find that you need to make this half as light as the kind of free-floating aluminium foil. So this is a very lightweight construction, but it looks like if you had enough nanotechnology, you could do this. And then you would be able to get most of energy from a star. In the case of the sun, that's about 10 to the 26th power on the watts, an unimaginably large number. And what do you use it for? Well, you could use it to power, of course, habitats where people or aliens are living. You could use it to power your computers. You could use it to send the laser messages. And remember, you have an enormous array here orbiting a star. If you put antennas across the surface, you have a potentially enormous radio telescope or radio transmitter or laser. And yes, you could use this to focus a lot of laser light on planets you don't like and fry them from a long distance. The problem with that kind of Death Star weapon is, however, that if the target is moving in a way you can't predict, you actually are going to have a hard time hitting them because, of course, they're light years away. So actually,
Space is huge.
Space is huge. And fortunately, it seems like even Dyson spheres, in all their awesomeness, are not enough to overcome this. So it's not like very, very good super weapons.
Right.
Unless you are really a sitting duck. Now,
Right.
the really interesting thing
So you'd
about
need to
this,
focus as well, right? You'd need to focus exactly on the point that you want to destroy. So it's like,
yeah,
I think you mentioned in another video that, like, it's like a teen or a young kid with a magnifying glass trying to focus the sun and burn ants, right? You can't,
yeah.
you need to really focus these things.
And it's an interesting thing in optics that the larger your magnifying glass is, or the larger your antenna, the tighter the focus can get. So obviously a Dyson Sphere would be really good for this. Most likely what you would like to focus energy on is not pesky neighbors, but actually on your own spacecraft to accelerate them away. So you can actually send spacecraft at close to light speed simply by pushing them using laser light.
Wow.
Yeah, so I made use of that in the paper that we discussed a while ago about settling the universe. And we found that it takes about an afternoon of sunlight to send off space probes that could reach all reachable galaxies in the universe. And
Right.
then another afternoon,
That's,
maybe the morning after having the party, to send off the probes to all the stars in the Milky Way. That's
yeah,
actually
yeah.
a bit harder because they're dust and gravel that you don't want the probes to collide with.
Oh, yes. Yeah, yeah.
So when thinking
Stopping
about,
these things is an engineering challenge.
oh yeah, so that is actually the biggest problem because when this little seed ship is being accelerated, it can get the push of an entire Dyson sphere.
These
When
are
you
von
want to
Neumann
slow,
probes you're talking about? Or...
yeah, so the original idea was coined by Bracewell, but von Neumann was talking already in the 1950s about the possibility of making self-replicating machines. And then Bracewell realized that's the way of settling the universe. He didn't think about going very long distances, just a few light years, but you can imagine having these robot probes going to nearby stars, mining material, building more probes, going to the next stars, and that way you can slowly but certainly settle the entire galaxy. But this kind of long-distance settling Stuart Armstrong and me analyzed in our paper seems to be the same thing, but now you get everywhere in just 2 generations. Much less risk of mutation or that cultural drift makes the probe decide to do something else.
I was so surprised when I found that out, that how much time it would take just to disassemble Mercury or something like that to create a Dyson sphere, but just the short time it takes actually to just send these things out. That doesn't take into account, of course, the travel time for it to get to these galaxies, but still, just the initial push outwards doesn't take all that much time at all.
Exactly, and this actually relates to something Freeman Dyson was thinking about in his book Disturbing the Universe. He kind of mentions this interesting thing that life might act as a kind of phase transformation of matter. So we have unliving matter, and if it contains nutrients, then of course life tends to gobble it up and turn it into living matter. Now, this might be true also on a cosmic scale. Right now, there is no life that can take asteroids and turn them into solar panels and the habitats and more life. But we're not terribly far away as a species from being that kind of life. We need to work a bit harder on automatic space mining, automatic manufacturing, and a little bit improvement of our space propulsion technology, and then we could in principle build this. We could be the kind of life that takes asteroids and turn them into space habitats full of humans and our kind of life, and then building further space habitats and at the very least settling our solar system. Now, the interesting thing Dyson pointed out is that this process is a bit like a phase transformation. It's like having water freeze. It turns into these weird ice crystals that are much more organized than the liquid. And it might be that life could have the same role in the universe. It starts out as a random disturbance, just as a kind of random grain of dirt in cooling water, acts as a nucleus for the ice crystal. But once the ice crystal starts growing, it takes water and organizes itself. Now, what Dyson did, he took this very far. He both pointed out that this is, of course, kind of interesting for thinking about our long-term future and how grand that could be, but also that this might actually determine the long-range behavior of the universe. Because if you just use standard astrophysics and look at the future universe, it looks fairly dreary. Basically, the stars are shining now, but eventually they go out. Eventually, we are left with little red dwarf stars that shine for about 1 trillion to 10 trillion years, and then they sputter and go out. And then you have eternal darkness, although there are still these objects, and white dwarfs slowly becoming black dwarf, neutron stars, black holes, a few planets. The galaxies drift apart from each other. Eventually they dissolve because of random encounters between stars. Eventually the black holes evaporate, and then you're just left with a universe full of elementary particles separated by enormous gulfs of nothingness. Sounds very depressing.
Yeah.
But what Freeman pointed out was, of course, well, we can start messing with this. We can build gravitational engines. It's not just using the current stars. We can actually make use of the fact that when stars pass next to each other, there is tremendous amount of energy involved in that. That can be exploited for doing actual work. He was optimistic that, of course, we can build fusion reactors eventually, and there's going to be plenty of hydrogen in gas giants and brown dwarfs. We can persist for a long, long time. And as the universe gets colder, life might also be able to adapt to this. He suggested what he called the biological scaling hypothesis, the idea that life might translate itself into other forms that could persist at lower temperatures. So this is a little bit like when debating whether minds and information processing can be substrate independent. Maybe it's possible that you can scan our brains and turn that into a software replica. So maybe our mental processing is substrate independent. Or at the very least, information processing really looks substrate independent. Even if you're skeptic of the possibility of brain emulation and uploading, you might say that, yeah, but those AI programs, they're actually thinking and have information. And of course, if you can run it on one kind of computer, you can run it on other kinds of computers. As the universe gets colder, you can use computers that use energy at a slower rate, but you have plenty of time and at very low temperature. So what Freeman suggested in the biological scaling hypothesis was basically that as the universe gets colder, you could always use lower and lower energy states. And the interesting thing is this might go on forever. So in his model, you have some amount of free energy, you use about half of it, and then you wait. You dissipate the waste heat that you got from error correction and all the other work you did as the universe gets colder and colder. And that means that the remaining energy gets more and more valuable, because now the contrast between your energy store and the background temperature gets stronger and stronger. So you wake up after a longer and longer time period, and now you use half of your remaining energy, and you do some stuff, and then you go back to sleep. And you don't notice anything, of course, because you just turn off the clock on your computer. So that way you might be able to do an infinite amount of computation across the future of the universe.
Infinite? Truly infinite?
Infinite. And this is, of course, where you get into the physical rubs and the naysayers and the interesting problems. So in Freeman's paper, he showed that under some circumstances, this is possible. The universe needs to be expanding at the right rate. If it expands too quickly, then you can't get hold of enough matter to actually persist indefinitely. And unfortunately, it looks like current cosmology is pointing in that direction. So this might not be possible. Other critics have pointed out that actually that alarm clock system you need in order to wake up at longer and longer time intervals is also a physical object. So very interesting quantum mechanical issues about making a sufficiently reliable alarm clock that wakes you up when you're supposed to wake up. So there are some pretty powerful reasons to think that this doesn't work as Freeman Dyson suggested in his paper. But it was pretty good going for a paper from 1979. And I think it has inspired many of us to think, what can we do given current cosmology? Personally, I think we probably can't get an infinite amount of computation done. The others disagree and hope that maybe we can make baby universes and go into them. Yes. I think we can just get a tremendously vast amount of computation done, and that's probably good enough. But I'm ready to stand corrected. If it turns out that my finitism is too pessimistic, well, so be it. I'm going to be celebrating with everybody else. But the really important thing he did was to show that information processing deep down seems to be physical. We're still groping towards a theory of the physics of information, but it does seem to be some very real leads in that direction. And informational processes are also very much what civilizations and minds are doing. It might very well be that there are important things our minds are doing that are not true information. I always get somebody complaining that consciousness or love is not really about information. And maybe it's true that the redness of red is not informing me about something. It's a qualia that is just sitting there. But certainly if I fall in love with somebody, I better know who that person is. There is at least some bits of information that better be in that feeling of love rather than a general lovely feeling. Love without information might be lovely, but that doesn't mean anybody is loving anybody in particular. Actually, information seems to underpin most of the things we find deeply meaningful and morally relevant. So even if it's not everything, it's a pretty good tracer of what we can do. If we can't do information processing, then we probably can't have consciousness or love either.
Yeah, that's something that I think the people at Qualia Computing and Open Theory are looking at right now. Yeah. So that's particularly interesting stuff.
And the fascinating thing is, of course, that information processing, by virtue of requiring a bit of energy, links the things we really care about, our emotions, our moral value, our thinking, our civilization, to physics in such a way that we can actually say at least a little bit about the limits and possibilities. So as long as we can't go faster than light, that means that we're kind of inside a certain light cone and have a certain amount of mass energy, and we can calculate roughly how many irreversible computations can be done. Now, it might turn out that we can do much more reversible computation than we believe is possible, which would extend our future tremendously. So that's definitely worth working on. If nothing else, because we probably want more energy efficient computers anyway.
Yeah.
It wouldn't do just having to build a Dyson Sphere because our computers are too wasteful. So we want to figure that one out anyway. But it seems like
computing, yes. Maybe some people aren't familiar with that. Yeah.
So normal computation, of course, wastes a lot of energy. So the computer that you're using right now is getting warm, not just because it's doing some calculations, but also because there are leak currents inside the silicon and a lot of bits flipping back and forth. And when we do that, a lot of energy is wasted. Now, in an ideal computer, that wouldn't happen, but there is an irreducible limit to how much computation costs, and that's sometimes called the Landauer limit. And this has to do with the second law of thermodynamics, the annoying one that says entropy always has to increase. So imagine that you have a bit. It's either 0 or 1, and now you want to erase it. So you want to have a fresh bit that is just 0. So you do an operation that erases that bit. Now you've reduced the uncertainty of a system from it could have been 1 or 0 to it's definitely 0. At this point, entropy seems to have gone down. And at this point, you need to pay the piper. Maxwell's demon shows up and kind of says, you need to give me some amount of energy to dissipate. It needs to be turned into waste heat and increase entropy. Otherwise, you have broken the second law of thermodynamics, and I'm not going to want to be in that situation. So basically, you need to pay a bit of energy. This is not an enormous amount of energy. It's something like 10 to the minus 21 joule of energy at room temperature. It's tiny. But of course, if you're racing a lot of bits per second because you got a really fast computer, this can add up to an enormous temperature. So actually, some of the earliest designs for nanocomputers that people came up with in the 80s, when you did the calculation, you realized that they would behave a bit like high explosives. They would just explode into heat. So they actually would require reversible computation, maybe running more slowly and avoiding increasing the entropy. So the idea about reversibility is that the computation can go in either direction. And that means you don't waste anything. So I might have my bit that I want to turn into a 0. And what I do is I just store it. I basically have I might put the information of that bit somewhere else. And now I get to have a 0 here. So I might have a big register here full of zeros. And every time I want to erase a bit, I just swap that for a fresh 0. This works really well. And I don't have to pay Maxwell's demon any energy. Everything is perfectly fine up until, of course, my set of zeros is depleted. At this point, I'm in trouble. So now I actually do need to pay energy in order to erase them. But I can do something really clever here. Many computations can be run backward. So I can run my computation. I fill up my register full of the bits I don't care about. But then I get my final result, which I copy and move somewhere else. And then I run my computation backward. I undo my computation step by step by step. This is not normally how we program. If you write in a normal programming language, you don't care about whether the operations can be reversed or not. But on a reversible computer, you can do this. And that means that eventually you get back to the initial state. So you only have the input information and a nice store of zeros. And at that point, of course, you can put in some new input information, and you do your calculation and then undo your calculation. This would allow us to actually do an infinite computation without wasting any energy. Except, of course, there is that darn little thing about error correction. Occasionally things go wrong, and at that point I need to erase the error, and I can't get away from paying up for that. So the amount of errors we do in a computation is actually the main limiting factor on how much future we have.
Oh, okay, right. That's
Yeah.
a fantastic description. But now this, back to what you were saying before about like civilizations going to sleep over, like strategically over periods of time. I think you've written somewhere else that might be a good explanation as to why we can't detect many other civilizations. Most of them are asleep at the moment.
Yeah,
For
so I have
strategic reasons.
So I have a paper called the aestivation hypothesis, which is a possible reason why advanced civilizations don't show up right now. After all, we haven't seen their Dyson Spheres and other activities. So in that case, where are they? So suppose you're a real advanced civilization. You've done most of the entertainment young civilizations do, and building a few Dyson Spheres and racing around the galaxy. And now you're mature, you realize that the physical universe is fairly boring compared to all the really cool computer games and mathematics and whatever cultural products you're doing. So basically all you're doing is computation. At this point, you will realize that the amount of fun stuff you can do is limited by the amount of energy. And the cost, of course, of fixing bit errors. And the Landauer limit is temperature dependent. So if you can run at a cooler temperature, you get much more fun stuff done eventually. The problem is, right now, the universe is a sweltering 3 degrees above absolute zero. It's really hot. You need to pay a lot of energy to run your computations, even if you're sitting out there in intergalactic space. But the universe is expanding and getting colder and colder. It's going to get really cold, of course, once those stars go out in a few trillion years. But it's also going to level out, because it turns out that there is a background radiation you get from the expansion of the universe itself. It's a ridiculously low temperature, 10 to the minus 30 Kelvin, which is unimaginably low. But that's kind of the lowest temperature you will ever get to naturally. So in this scenario, advanced civilizations decide to sleep in until the universe is cold enough. Because basically every ounce of energy they have will become 10 to the 30 times more valuable if they spend it in the far future. It's a bit like an investment thing.
Right,
So
yeah.
the only thing
So
you
if we
need to...
use it now, we're wasting a lot of the future energy. Is that right?
Yeah. Every piece of energy we're using right now could have been used to 10 to the 30 times more computation. Again, it's very hard to even imagine how much computation that is. It's much more than has ever been done by all the humans and computers on Earth. Every time we use even a simple computation, we're wasting what could have been an entire civilization's worth. So if you're a kind of computation-centric civilization, you might say, okay, wake me up when it's cold and crisp, and you get to kind of the autumn of the universe when it's harvest time, and you can actually spend now quadrillions of years having fun and doing whatever advanced civilizations really do. So this is the aestivation hypothesis. We don't see these civilizations because we're all sleeping. Now, it's a fun hypothesis. You can kind of make links here to H.P. Lovecraft's ideas about the great old ones. The old super gods, they're asleep, and one day they will wake up. Another interesting thing is, of course, it hinges on a whole bunch of assumptions. So it's very fun to follow through with them. Some of it has to do, of course, with computation. If it turns out that you can do computation without paying energy, in that case, actually, this doesn't make sense. So there is a paper criticizing me, and I'm trying to write a counter paper to that, analyzing this. So it gets into these core questions about what is computation really, and how much can we stretch it. Another important thing is, can you protect your stuff from other civilizations, especially a civilization that might just evolve in your stuff? It's a bit like putting clothes into the storage, and next summer you discover that mice have set up living in the pockets of your clothes. We might be those mice. So one interesting thing is that this scenario assumes that you probably have some robot guardians keeping an eye on things. So if we do certain things, they might slap us down or just tell us that don't mess with this. This is ours. So it actually suggests we might want to watch out for something. It also suggests that presumably astronomical processes that waste a lot of these future resources should be inhibited somehow. Because if you're trying to estimate, you don't really want your equipment and your resources to disappear. So that leads to something observable. We should be looking around and try to see things that seem to be wasting useful resources. Are they unexpectedly inefficient? Is there something that prevents that? And this actually gives the strongest argument that this probably isn't a true hypothesis. Because there is actually a lot of waste going on. Some people would say, yeah, all the stars shining, they're wasting tremendous amount of energy. But that's just a tiny amount of the energy inside a star. Fusion can only burn about 0.7% of the total mass energy. That's a tiny fraction. The white dwarf that gets left behind, if you can feed that to a black hole, you can get up to 42% of the mass energy. So the loss of starlight that's not really worth it unless you're really, really green and meticulous. A much more serious thing might be, however, that we're losing tremendous amount of gas from galaxies that is basically going out into intergalactic space and then falling away because of the expansion of the universe. And this might be so much that up to 50% of all the baryonic matter we have. And then there is the dark matter. Because, of course, we're just about 1/5 of the matter. The dark matter doesn't seem to be that useful, but we don't know. Maybe that is really valuable. Again, we seem to be losing that as it's sloshing around. And there doesn't seem to be any process of keeping it in place. So I think there are good reasons to think that nobody's estimating close to us, at least. Nature seems to be behaving in its normal, beautiful, wasteful way, which might be a great opportunity for us, of course.
Right, of course, yes. But what do you think of other people's idea that of creating baby universes, or using some kind of, I don't know, black hole engineering to birth engineered universes that are ripe or fantastic for computation, that are like optimized for computation and at any temperature?
That would be really great, but it's also much more speculative. And at this point, I'm pretty certain some of the viewers are coughing up their tea because, wait a minute, that's too speculative for me. But I think there is a difference here in how speculative you can be about things. So a lot of extrapolations about the far future of the universe are just based on standard astrophysics that we test every day by trying to predict and retrodict what's going on in the universe. So we actually have a pretty good idea what stars are doing and how long they're going to last. Predicting things about the degenerate era, where you have white dwarf stars and neutron stars in a cold future universe, is harder and more uncertain, but it's still based on a lot of physics we kind of understand. Hawking radiation and evaporating black holes, well, theoretical physicists are pretty confident, but we don't know that for certain. Now, making baby universes, on the other hand, requires probably new physics, or at least physics we know we don't know yet. So the basic idea that has got serious physicists to propose this is that quantum gravity is a thing. We know general relativity that describes space-time and black holes works pretty well on the large scale. And we know quantum mechanics definitely works really well on the small scale. And they're totally incompatible as theories. The math doesn't add up at all. It's pretty clear that something needs to bridge them. There is some way the universe actually does this. And in particular, as matter collapses into the singularity of a black hole, that's pretty clear that, okay, something is going to happen there. and our current theories can't predict it. So there are some models in string theory and related theories that suggest that you get local inflation, you get a little baby universe. The matter going into that black hole causes inflation and probably an unfolding of a new big universe, which might also have laws of physics that are kind of random. It's important here to realize that it's not completely free how you set up the laws of physics. Again, philosophers and physicists have been having great fun thinking about what are possible worlds like. And there are some philosophers who even go way beyond what physicists believe in. There is something called Meinong's jungle, named after an early epistemologist who suggested that when I talk about unicorns or square circles, they actually do exist in their own worlds. And this is not just odd things like unicorns, but things that are totally self-contradictory, like square circles. Most philosophers say, yeah, we're not going into that jungle. So they think that maybe possible worlds need to be somewhat sensible. You probably can't really have a world where 2 + 2 = 5. As any mathematician will tell you, well, that's an inconsistent system. Anything is allowed there. So everything and nothing happens at the same time, which seems to be not much of a world in the first place. On the other hand, we can imagine worlds like ours where the fundamental constants of physics have slightly different values. Indeed, this is quite natural given what we currently believe about the Big Bang process, because it seems like many of these constants were set by symmetry breaking. There is no fundamental reason why they need to have the value they have. It's just that they ended up like that. This is kind of okay if you believe that the universe is very large, so there could be parts with different values, or maybe even that there is a multiverse. If you think there is only one universe, you have a hard time now explaining how we got values that actually work well with creating a complex world with stable matter and intelligent observers. But if a universe is big enough or we have a multiverse, this is totally fine. There might be observers only in a tiny fraction, but that's all right. So now if baby universes emerge, they get symmetry breaking anew, and they might get new constants. And some of them might actually be better, of course, for doing information processing than our universe. It's kind of a tricky question here, whether this would be useful for anything. Because first of all, can we really control that symmetry breaking? Well, we can maybe control how matter collapses into a black hole if you're a sufficiently smart super civilization. But it might just be that fine-tuning it so you get symmetry breaking going the right direction is super hard. Or it might even be that we can prove that it's quantum mechanically impossible. The uncertainty relations in quantum mechanics actually put a limit on how much we can place things where we want them. It might also be that, yeah, maybe we can make universes with designer settings of the laws of nature, but we can't go there. So maybe these universes get their own inhabitants, but we can't really send a message to them because basically the throat of a black hole or the wormhole connected to that universe doesn't allow us to send many bits of information. Or it might be that we can send some information, but it's finite, which means that you have a packing problem. How much of the luggage of your super civilization can you afford to throw into that black hole? So this is really speculative, and it's an interesting issue also from an ethics standpoint, because what's your moral responsibility of doing this? If you just believe you're making random universes, you might already have a pause here, because if the average random universe is a bad place, maybe we should refrain from making them. I'm kind of optimistic. I think actually most universes or the observers are probably awesome and interesting. So I would probably go for making a lot of universes. But I'm not certain about this. I could be the greatest moral monster ever if I made a lot of universes without actually making them good. So it would be really useful for us to understand physics much better before we seriously try to do this. Fortunately, we don't have any nice desktop black holes for us to throw stuff into yet. But the question might come up, and we certainly might have to think about it, about our virtual simulated universes we're making in our computers.
Yeah, that's interesting. I wonder if there's any sort of signatures that around black holes, once we understand them, if there are some sort of mega scale engineering about optimizing black holes so that aliens can escape into paradises of computation, then maybe we can see some sort of like evidence around surrounding the black holes, or maybe all that just gets sucked in before we get a chance.
I think it's likely that you will not be able to see that process. If you actually have aliens doing it, it's probably going to be a quick process. But we might see other things. So Dyson originally suggested a Dyson shell surrounding the sun because we have the sun within reach. But you could get much more energy out of a black hole. So what you could do is you take a big black hole with an accretion disk of matter, and then you throw your garbage in, and it turns into plasma, and it radiates away a lot of its mass energy as X-rays. Now, let's build an ultimate Dyson sphere around that. So a normal Dyson sphere, I mentioned earlier, you might make one of very, very thin aluminum foil. It has to be made in space because it's so thin that it would rip because of air currents on Earth. In this case, you want to go for tungsten, and you probably want to weigh it down because the radiation pressure from a hefty accretion disk is actually big enough to keep lead floating away because of the radiation. But you would get so much energy. And there are other ways of tapping black holes from energy too. There's something called super radiant scattering, where you basically use mirrors around black holes to have energy sloshing around, and you can get tremendous amount of energy released very quickly. These kind of engineering projects, I don't know exactly how they would look like, but you might want to look for spectral lines that look out of place. So, for example, tungsten or tantalum hafnium carbide or lead, they're not the most common materials in the universe. In fact, you mostly get them from colliding neutron stars splashing neutronium that turns into heavy elements. You don't even get them from garden variety supernovas. So you need to carefully capture them and then put them into your systems around the big black hole. This would suggest that if you look at spectral lines around black holes and see a lot more of these very heavy elements than just normal stuff like nickel and iron, you have a hint that somebody's doing weird engineering over there.
Well, indeed. It kind of made me think, there might be processes out there. I imagine, like, if aliens thought that there was a reasonable degree of likelihood that they had neighbors, or if they realized that they had neighboring civilizations, that might sort of change their behaviors in a way that they'd exploit more energy in order to quickly ratchet up the power of their civilization, in which case there would be a load of evidence out there that there are civilizations, or they might just try and hide.
Well, yeah, so in recent years, people have been very happy with that. Oh, maybe we're all hiding hypothesis, partially because of some excellent science fiction novels. I don't think that is stable, though. I actually have a little paper where I was looking at von Neumann systems, self-replicating machines. What if everybody's hiding because there are interstellar killing machines out there? So if you make a noise, something comes and attacks you. And it turns out that this is unstable, because if two species have made systems like that, then these machines are of course going to try to kill each other. And then the logical thing to do is use more energy to build more machines. So the end result is everything gets turned into these machines, and that would be very, very, very noticeable. So it doesn't look like that is going on. So I don't think the hiding strategy is stable. Similarly, sending messages to advanced civilizations, it might be that once you're sufficiently advanced, just started on your first Dyson sphere, you could easily send messages to anywhere in the universe that can receive the messages. It might be that you don't need to go very extreme to send these messages. It might be more a matter of patience. How far away are they? And that, of course, gets to the more boring answers to the Fermi question, where are they? Maybe the universe is just sparsely inhabited. So when I wrote the aestivation hypothesis paper, that was based partially on what we might want to do as a civilization, but also if there is a lot of civilization, why are we not seeing them? But another way of reasoning might be maybe there are just very few civilizations. And I try to look how we actually could estimate this. And normally when talking about it, people bring up the Drake equation. So the Drake equation is basically the number of sites in the universe where you could get planets that could be habitable, times the fraction of habitable planets, times the fraction that gets life, that gets intelligence, that gets communication from intelligence, and how long we live. And then we all start bickering about sensible values of these the factors. And as Jill Tarter said, it's a wonderful way of organizing our ignorance. But many people are making guesses. And it's nice because we actually know the value for some of the early astrophysical terms rather well. But we're very uncertain about the probability of life and the probability of life producing intelligence. And we really care, of course, about how long does intelligent life last. That is why I got involved in the first place, because my work at the Future Humanity Institute involves in thinking about how do we ensure that we're staying around for a long time. Now, the interesting thing is, if you plug in numbers here, and many people do that, and then they say, okay, I don't know this value, but I'm just making a guess here, and let's accept that this is a very crude guess. Then you end up with a number at the end. And then you typically say, oh, this is a guess. But you don't really know how uncertain it is. And that actually turns out to make an enormous difference. So I wrote a paper together with Toby Ord and Eric Drexler called Dissolving the Fermi Paradox. And basically, we found that if you actually calculate uncertainties carefully and use uncertainty intervals, you end up with a probability distribution that has some very funny properties. So we might put in averages that are actually very optimistic. And then you get an average out saying, oh yes, on average, we should expect 1 million civilizations in the Milky Way. We're basically in the Star Wars galaxy. There are aliens on every moon, more or less. However, that probability distribution, based on the uncertainties we had, also get a long tail leading towards more pessimistic outcome. So the median case, what you actually would expect most often is maybe 100 civilizations. And you get up to a third of a chance that we're alone in the visible universe. Now, why does this happen? Well, we're really uncertain about the probability of getting life on a planet. Literally hundreds of orders of magnitude of uncertainty. This is way more than we're normally dealing with. When talking about winning the lottery, we're just a bit uncertain about a factor of 1 million. But this is literally millions and millions and millions and millions and so on uncertainty. And that means that we can't rule out that we're very lonely in the universe. Now, the fun thing is, of course, this is based on current best science. And if we start discovering, let's say, microbes on Mars, we will say, oh, we now get much less uncertain, the probability distribution update, and we can say something sensible. The really nice thing about this, though, is it makes us less afraid of a silent sky. Because many people have been looking at the empty sky and saying, oh, maybe the reason we seem to be alone is that civilizations don't last very long. That's called the great filter argument. We know that at least one of the factors in this equation has to be really small. And if it's one of the early ones, like life being very rare, or that maybe complex life doesn't happen, in that case, we're kind of golden. Yep, we're lonely, but our future is pretty unbounded. But it could, of course, be that intelligence, as soon as it comes about, discovers something terribly dangerous and destroys itself. And that's, of course, what the more gloomy thinkers think is like. What we can show using a fair bit of math is that given what we know about this uncertainty distribution and that we're not seeing any aliens, most of the update is leaning towards the early terms. The fact that I didn't see any UFOs in a mist parked on the street today in Oxford is actually giving me super weak evidence that we can't be living in a universe that's absolutely crammed with civilizations. That lowers all of these parameters, but it lowers the most uncertain ones the most. So the rate of star formation in the Milky Way, I don't need to update that because I don't see any UFOs, which is as it should be, because that would be totally crazy. The slightly less uncertain, slightly more uncertain parameters like number of habitable planets per solar system get a slight nudge downwards, but it's a slight one. Similarly, for the longevity of civilization, we have 7 orders of magnitude uncertainty here. It could be that we only last for 100 years. It could be that we last for billions of years. But actually, it gets nudged down a tiny bit, but not much. Meanwhile, probability of life and probability intelligence, they move down a little bit more. So this gives us a reason to hope that actually the silent sky isn't that scary. The stars are not foretelling our doom. We still need to get out there and figure out what's actually going on, of course.
Did you hear in the news that they'd found protein structures, not just amino acids, protein structures within meteors? It's just a very recent thing. I don't know how much fact checking has been going on, but I thought that might increase the likelihood of life in the universe.
Yeah, so the paper is just a preprint right now, so we'll see whether it gets through peer review. And I wasn't terribly impressed by it as a protein. It was still a pretty simple molecule, but way more complicated than what I would normally expect to find in a rock. So I think the chemicals that could make life are probably found in way more places than we normally think. And there is an enormous amount of weird organic gunk out in the outer solar system. The brownish and reddish spots on the surface of the outer moons, that's organic gunk.
Wow.
Now, if it existed on Earth, it would be a bit like tar. And over here, there are certainly bacteria who would be very happy to chew on that. So I don't think it's unlikely that there could be life out there. There is another interesting thing here, and that is that it might be that life is common, but advanced life is very uncommon. One reason is that life here on Earth has evolved rather rapidly. It only took us about 3 billion years to become multicellular and start getting nervous systems and starting to crawl up on land. Maybe that is really fast. We could imagine genetic coding systems that are much slower and produce life that takes trillions of years to evolve anywhere interesting. At which point, of course, their star has burned out long ago, so they don't get anywhere. This is something we don't know yet, but this is something that can actually be studied in the lab. We can actually do exploratory chemistry and exploratory biology figuring this out. And we should, of course, be sending probes to the different planets in the solar system to try to see what about Mars. Mars, Earth, and Venus have been exchanging pieces of rock for a long time, and there is a good chance that if they could have life, at some point they could have infected each other. It might be that it's possible that the life could subsist in weird environments like the moons of Jupiter. It might be also that it could be a really exotic life on Titan. Now, the important difference here is that if there is kind of Earth-like life, in the sense that it uses our amino acid on Mars or maybe in the oceans of Enceladus or Europa, that just shows us that life can become rather common and spread by asteroids. If we find that there's some weird thing based on methane and ammonia on Titan, that shows different kinds of life are possible, and probably life is very common in the universe. That would be kind of scary news for us, because now the great filter turns into, okay, intelligence or short-term survival. But it's going to be fun finding out.
Oh, indeed, yes. They're going to be drilling into the valleys in Mars where a lot of methane seems to emanate from. And if they do find some sort of basic life then, and that basic life sort of has a genome or something that's completely separate from our own phylogenetic tree, like a second tree, then that would speak volumes to the likelihood of other forms of life out there, other seeds of life, wouldn't it?
Exactly. And another important thing is, of course, we might want to look here on Earth and see, is there a dark biosphere of other kinds of life? Right now, we're doing a lot of metagenomics. You scoop up a liter of seawater, and then you use PCR methods and other forms of bioinformatics to see what kind of DNA and RNA is there. And this way, you can kind of get hints of the actual diversity of life on Earth. But what if there was non-DNA based life? Maybe in small niches. We would not be able to pick it up on PCR. So it might be rather tricky to find. And many people think it's very unlikely that it would have been around. But that's another interesting form of xenobiology you can do right here on Earth. It's just the tricky question of how do you find that one kind of bacterium isn't like the other one?
Oh, indeed. Yeah, yes. Well, I mean, where do we go from here? Do you think Kardashev? Yeah, sorry.
The Kardashev scale, yeah. So another pioneer in astrobiology, or especially SETI, is of course Kardashev, who also sadly passed away a few months ago.
Yeah.
And he had this brilliant paper, which is kind of the other main pillar of what I would call the Dysonia school of SETI, where he was bringing up what's now called the Kardashev scale. So he pointed out again that there might not be any limit to the size scale at which civilizations do stuff. But we might want to look for the energy emissions. So he suggested that level 1 civilization was using the energy resource of one planet. A level 2 civilization would be using the energy resource of a star. And of course, the
Like
example
Dyson
gave,
Spheres. Yeah.
exactly. And a level 3 civilization would be using the energy of an entire galaxy. And you could imagine having Dyson spheres around all the stars and maybe englobing the black holes and things like that. You can even imagine a level 4 that would correspond to the accessible universe, all of it being used in some sense. And maybe a level 0 corresponding to a civilization that is just using its own muscle power. Now, the interesting thing about the Kardashev scale is that this suggests something we might want to look for: energy emissions. And this is something the astronomers are good at. So they can point telescopes at things, they can look at various forms of radiation, try to see, are these energy emissions looking a bit like what we would expect from a civilization? Now, the tricky part here is it's not given that you actually would get civilizations that neatly sit on these thresholds. After all, we're kind of half of a level 1 civilization. We're not fully using all the energy on Earth. We're doing a slightly haphazard job of even that. And yet we're producing some emissions, so in some cases literal emissions, that would be detectable using spectroscopy. The Earth's atmosphere has a lot of really weird molecules and chemical imbalances that hint that at least there is life. And if you start looking for things like fluorocarbons, that's unlikely to be produced by normal biology. That kind of requires factories and refrigerators and things like that. Now, the interesting thing about both Kardashev and Dyson is that they were thinking about civilizations as natural objects. Normally in astronomy, we think about nebulas and planets and stars as natural objects. But of course, a biosphere and a civilization are in some sense just as natural. They're just very weird phenomena. So far, we haven't seen many examples of them. And they're phenomena that have certain characteristic properties that you might actually develop some kind of physics to understand. Biology would, of course, say, hey, this is called biology. But we want something that works for all kinds of biospheres, not just the one we got, but for maybe all the generalized life in the universe, whether that is carbon-based or methane-based or silicon-based. This kind of generalized activity, and that's probably best described using information processing and some of the more abstract forms of thermodynamics. This is the area where actually physicists and biologists and astronomers have a lot of interesting things to tell each other. But it takes a really visioneering mind like Freeman Dyson's to realize this. People are certainly thinking that maybe life could be based on silicon, rather than thinking, what is life? Erwin Schrödinger, one of the pioneers of quantum mechanics, was brilliant enough to actually ask that question in his seminal book that started this process. And similarly, Dyson then went on to ask weird questions like, what are the limits to what life can do? Maybe we can treat life as a phase transition of matter. What are the kind of physical phenomena we should expect from that? So I think the really interesting thing here is, could we develop this kind of science of complex systems, not just complex systems as chaos and self-organization in the lab, but as biospheres and technospheres on the largest possible scales?
Oh, indeed. I imagine you have some really interesting conversations with some of your colleagues about this, about the Fermi Paradox and why there's not many people, not many civilizations that we can detect out there, or not any other than their own. um, how do you respond to some of your colleagues' seemingly more pessimistic views on the reasons why there's no other civilizations that we can detect and what we should do about it?
So I think the Fermi Paradox is interesting because whatever the answer is, it's kind of mind-blowing one way or another. If we're alone, that means we're in charge of the universe for good and ill. That's an awesome responsibility. If it turns out that civilizations don't survive very long, that suggests that there must be existential risks out there that are very hard to avoid, even when you know that they exist. That seems to be a very weird kind of risk, because right now we're realizing that nuclear war is no good and maybe we want to make safer artificial intelligence. That's not easy to fix, but it's not hard to imagine a world that was slightly more sane that could fix these problems. So the kind of risks that are required to really reliably wipe out civilization need to be actually quite strange. It could be that you have some version of a zoo hypothesis or the aestivation hypothesis. There are great old ones out there. Maybe they're sleeping in, but the robot police are kind of keeping an eye on us. That's also kind of a mind-blowingly weird situation. Or it could be that the technology ceiling is really low. Maybe we can't do very advanced technology, which is kind of strange because many of the technologies required for even these radical things I've been talking about right now are not terribly far away from what we're doing. Remember, we're launching satellites that form a super primitive Dyson Sphere right now. We are building automated manufacturing and mining because we're interested in 3D printing and cheap mining. Those robots exist today, and it seems implausible that you couldn't make better versions of them. So assuming that the technology ceiling is so low that civilization can never get out from their planets, for example, seems to be a very weird claim too. So practically all the ways out of this seems to indicate that something is really odd. And it might be that we're totally missing something that will be dead obvious when we get it about the whole way we're framing these questions. But that's also an exciting possibility, that we don't know what we're doing at all, and we can yet be aware of that. It's a bit like quantum gravity. We know something doesn't fit here, and the day when we finally get it to fit, that's going to be amazing.
Indeed. So what tractable and underpopulated areas of research do you think would provide a lot of bang for buck, so to speak, in any area trying to make sense of the reason why we're alone or seemingly alone, what we can do to increase the likelihood of survival and becoming a mature technological civilization that's not prone to existential risk?
So I think kind of following the steps of Freeman Dyson, because he actually wrote a fair bit about this. Some of it is kind of obvious. Yeah, we should be doing a lot of research to reduce existential risk. That's kind of useful because if we die out now, we flub it and we don't get this grand future. But it seems that there are certain technologies that would give us a lot of useful stuff. So settling space might not be the most cost-effective way of fixing existential risk right now, but it's a wonderful motivator for solving tough engineering problems for real. So building automated mining, automated manufacturing, effective forms of solar energy or even nuclear energy, that's super useful for space. But it's kind of useful down here too, because if you can build something that can actually construct a livable environment in space, you can use that in the much nicer environment on Earth to make a livable environment using renewable resources. So when you think about a closed ecological life support system in space, that only takes in sunlight and maybe some inert rock material and allows the recycling of material on the inside. That would be a really useful form of agriculture on Earth. We probably want to do agriculture in totally different ways down here, but it's an existence proof that you could actually do 100% sustainable agriculture forever on Earth. That's worth a bit. And it might be easier to get funding for the space stuff because you get the magical fairy dust of space there rather than the staid normal questions about how do we help sub-Saharan Africa. Similarly, automating manufacturing and mining are very useful things for handling our own resource crisis, especially when you can use solar power to power robots and other equipment to make more solar power and robots and equipment. Obviously, we have a bit of a safety issue here on keeping control over those systems. And Freeman Dyson had an interesting point about advanced civilization. He pointed out that one of the biggest problems might be sanity. You actually need to figure out the science of being a sane civilization. I don't think we can call ourselves a sane civilization right now.
Great.
It's not just that we're kind of just out of the caves and we have just barely started with systematic ethics and we just discovered that ecology thing very recently and we very recently realized maybe we should keep our climate stable, etc. It's also that we lack good coordination mechanisms and we're probably missing a few profound insights. And general, our mental stability, individual and collectively, is not the greatest. These are things we can actually work on. These are actual real projects. Both figuring out better ways of handling our own mental illnesses. It's shocking how many humans are suffering from depression and cannot contribute and do something good about their own or the collective future. But also about our coordination abilities. We have international institutions that are relatively toothless in many cases. And we need to build the tools to one day be able to coordinate well about things, whether that is pandemics or making safe AI code, or how we want to go about doing traffic control for the emerging Dyson Sphere. So I think Freeman Dyson was right about this, that sanity engineering might actually be one of those ultimate technologies we need to work quite hard on. And it's very different from what we previously worked on. We know how to do engineering of steel and energy and even information, but we might need to do an engineer of meaning too. But that's an amazing challenge to start working on. I think the potential is literally infinite in all directions.
Well, my mind is blown. I really like what you've just said about sanity engineering. So, look, there's been a lot of ground covered in this interview, and thanks so much for joining us and spending the time to talk to me.
Well, thank you for having me.
Yeah,
it's been a delight.
Yeah. And I forgot to mention at the start of this, which I might sort of tack onto the start, is that it is Future Day, everybody. So if you're wanting something to do on a March the 1st in future years, then organise an event at your local pub or your local community space and talk about the future. So is there any other concluding statements that you think that you'd like to contribute to wrap up the conversation?
So I would like to add one concluding statement to this, and that's about Freeman Dyson as a person. So he was quite often a very creative thinker, coming up with radical ideas like the Project Orion, nuclear explosion-powered spacecraft and other things. But he was also quite willing to be contrarian. He was one of the first people who did actual modeling of anthropogenic climate change back in the 1970s. But in recent years, he's been known as a climate denialist because he was kind of having his own opinion, which didn't sit well with the consensus opinion. But the thing that made him so wonderful was the kindness. He was actually willing to listen to dissenting opinions. He might certainly argue against them, but he was always willing to actually listen to dissenting voices if they had something worthwhile to say. And I think that's a great way of honoring his memory, actually, to realize that, yep, there are people who disagree with you. Some of them might be very smart. They might still be totally wrong. That doesn't mean one should be rude about it. That means you should just check what's going on here. Does this make sense? And then if it makes sense, well, then maybe one should change one's mind. And if it doesn't make sense, well, kindly point out where some improvement might be needed.
Indeed. Well, it is sad that we've lost great minds like the likes of Freeman Dyson and also recently Kardashev as well. But I am happy that we do have some brilliant minds still around, like you, Anders, and also, I should say, others at the Future of Humanity Institute, which is a really hotspot of very high impact philosophy and work being done there. So if anybody...
We're doing our best. Hopefully some of it is useful.
Yeah, I'm sure you're doing the best. And I think if people were trying to find a place to donate, FHI would be an excellent candidate too. So yes, please consider donating to the Future of Humanity Institute, and then they'll be able to amplify their best, which is...
Thank you so much.
Yes, so thank you so much, Anders. It's been great talking to you again. Cheers.
Wonderful. Towards the future.
Towards the future.
Yeah.